Hi everyone, I'm Manos Hadzakis from EPFL, and I will present our work on distributed data series similarity search. Odyssey is our framework that successfully addresses various challenges of distributed similarity search, proposing scalable distributed query scheduling and load balancing, while it gracefully navigates the trade-offs between memory limitations and query answering performance. Data series, defined as data points ordered along a dimension, have multiple real-world applications across virtually every scientific and social domain. One of the most promising methods to extract knowledge from data series is similarity search, which, given a query with a data series collection, is a task of locating the most similar data series to the query in that collection, and it has a pivotal role for data series processing. Nowadays, we face some critical problems. As petabytes of data series are produced daily, it's impossible to fit big data collections in a single machine, while the limited memory size has made the fast in-memory processing more challenging. In addition, the increasing need for availability in modern applications set the single machine parallelism inadequate. This is why shifting to distributed processing is crucial to address these problems. Unfortunately, distributed processing has challenges that we need to overcome. The first challenge relates to query scheduling, as we need to decide which queries will be assigned to which nodes of the system. In order to perform efficient scheduling, the data should be replicated, while we also need estimations about how hard is each query based on its execution time. The second challenge is load balancing, because we need all nodes to perform useful and equal work. We need to create algorithms that distribute the data fairly, distributing the good answers equally over the system. We also need to handle inaccurate estimations and enable nodes to help each other. Odyssey proposes mechanisms that efficiently address those challenges. Our framework can generate query hardness estimations and supports flexible data replication schemes that enable scalable dynamic scheduling. In addition, Odyssey addresses load balancing by distributing the data in a density-aware manner, ensuring that good answers will be distributed fairly across the system. Moreover, the framework utilizes a novel single-node similarity search algorithm that allows efficient query answering and work-stealing opportunities. Overall, Odyssey utilizes all those methods to successfully address the distributed challenges. To answer a query, each node builds an in-memory index based on its local data and performs a traversal over the index to obtain an approximate answer, which is called first BSF, best so far. BSF is later used during exact search, where all index is processed in order to prune regions of the tree, while we update best so far every time we find a better answer. Throughout query answering, the distances of data series less than best so far are stored in priority queues, which have a size threshold. When a threshold of a priority queue is reached, we create a new one. To be able to monitor the origin of each priority queue, we split the index into subtree batches, generating the corresponding priority queues according to each batch. The single node algorithm design is crucial to accommodate our work stealing, which we will present later. To determine the priority queue threshold for each query, we noticed that there exists a correlation between the first BSF and the median size of the priority queues produced for answering it. Thus, to determine the threshold, we fitted a sigmoid function to our data, and we used the generated value of sigmoid as our threshold. After the priority queues are filled, we sort them in a single array in order to bring the most promising priority queues first and be able to do a lot of pruning. So, let's see what would be the simplest solution to shift to distributed processing. We begin with a system of four system nodes, and we have a dataset which we will split in as many chunks as the available system nodes. Each system node will be assigned its chunk in order to build a local index. Then, to answer a query from a query batch, we would need to answer the queries one by one, forwarding each query to all nodes in order to search all the datasets. Each node would process the query based on its local data, and the answers of all nodes would be gathered to select the best one. So, did we solve the problem? Well, although the SQL split method enables the in-memory processing of large datasets, it suffers from several shortcomings. First of all, the naive chunking-based data partitioning sometimes may lead to imbalances between the workload of the nodes. Think of a scenario where all good answers are stored in the same chunk. The node processing this chunk will have a lot of work to do, as it will do less pruning due to the fact that it will need to calculate the distances of all good answers. In this scenario, all other nodes will remain idle, unable to help. In addition, this approach does not lead to scalable query answering. As nodes operate in different subsets, all queries should be forwarded to all nodes, not allowing any scheduling. Also, since each node stores different data, it is not impossible for nodes to help each other in case of imbalances. Thus, sophisticated data distribution and data replication schemes are crucial in order to support scalable query answering. Odyssey tackles the challenges in the following manner. We start from the same system of 4 nodes with the same data series dataset, but the dataset is now preprocessed by our density-aware partitioning algorithm that fairly distributes the data over the system. Our algorithm achieves that by calculating binary summarizations of the data series and groups them in buffers according to their summarization code. Then, it reorders the buffers into an alternative ordering according to Gray code. We do that because Gray code places similar buffers close to one another, enabling us to easily assign their data series to different system nodes in a round-robin fashion. As a last step, we select the number of partitions, and the algorithm starts by partitioning the largest buffer first before partitioning the smaller ones. The process is repeated till we have 2 balanced partitions for our scenario. This way, we manage to distribute the data series fairly, ensuring that similar data series won't end up in the same node. Since we selected to create 2 partitions for this example, the density-aware algorithm generates 2 data chunks. In Odyssey, we replicate those chunks to several nodes. In this example, chunk 1 is replicated to nodes 1 and 2, while chunk 2 to nodes 3 and 4. Now, we have sets of nodes sharing the same data, and we have created what we call replication groups. This replication strategy of our framework is important because inside the replication group, query scheduling is possible. To answer a batch of queries, each replication group loads the queries and answers them using a scheduling algorithm to execute them in the most efficient way. In addition, to enhance the performance, nodes in Odyssey share their best of Rs through a common best of R sharing channel to provide the rest of the system with possible good answers. Then, each application group generates the answer for its query, and those answers are collected to generate a global answer for every query of the batch. To schedule the queries, Odyssey performs dynamic scheduling using a coordinator node which assigns queries to the nodes of the same replication group when they are available. Also, to enhance scheduling, we would like to have query hardness estimations in order to schedule hard queries first and assign the rest of the work to other nodes. With estimations being available, we can perform even better scheduling. To generate the estimations of execution time, we correlated the first best of R and total execution time of its query and performed a linear regression. However, regression can many times generate inaccurate estimations and lead to suboptimal scheduling. For example, a scenario where a hard query is misunderstood for an easy one and gets scheduled last will be problematic, as the node that will be assigned to it will be the only one working in the end, leading to imbalances. This is why we need a mechanism to handle these exceptional cases and thus ensure good performance under all conditions. This mechanism is a novel work-stealing algorithm which operates within each replication group. When a node has finished its own work and no other queries are left, it helps other nodes of the group by recreating their priority queues that would be processed last as they contain the least promising distances. This helping scheme is efficient in practice and requires minimal data communication over the network, as the only information exchanged between the nodes is which subtree batch the priority queue belongs to. Our experimental evaluation was performed using a cluster of 16 nodes that had 200 gigabytes of available memory each and 128 available cores each, and we utilized several datasets of varying sizes. The first graph here presents a comparison of multiple Odyssey variations with other competitors for 100 gigabytes of seismic data. The x-axis represents the number of the nodes, while on the y-axis we report the total query answering time for a batch of 100 queries. The variations of Odyssey we used are the naive equal split, the no-replication case with a density-aware distribution, and the full replication version of Odyssey, where all nodes load all data. From the graph, we see that all variations of Odyssey manage to outperform their competitors, and that Odyssey can be more than 3 times faster than its best competitor. This second graph represents the query answering performance of Odyssey for multiple replication settings for 100 queries of seismic data, starting from no replication to full replication. X-axis represents the total nodes in each configuration, while Y-axis reports the total query answering time. As we see, when any replication setting is used, faster and scalable query answering is achieved. This last graph presents the throughput of Odyssey for 100 gigabytes of random data and multiple query workloads using full replication. We see that Odyssey performs highly scalable query answering with linear speedup for different query batches. To summarize, we care about distributed data series similarity search because it has many real-world applications and it is a hard problem with several intervening challenges. We presented Odyssey, a framework that addresses the distributed challenges. It achieves significant speedup compared to competitors, and it is able to navigate the trade-offs between memory requirements and query execution time. Thank you very much for your attention.